This is screencast 3.7 for AP Chemistry, oxidation number. There's two slides that show the exact same thing, so I'm going to show both of them, and it's a bit redundant, but you can use some of them as a self-test. So perhaps learn on the first one, self-test on the second one. Why do we have oxidation number? If you're doing chemical reactions, mass balance is so important. If you start with 100 grams, you're going to end up with 100 grams somewhere, right? You might have unreacted material, you might have outgases, but it will be mass balanced. It will also be charge balanced, right? If it's uncharged in the beginning, it's uncharged in the end. If you're dealing with ionic compounds and you're trying to keep track of the charge, that can be pretty straightforward since the charges are specified. But what about if you have methanol, or if you have some kind of a chromate ion or something like that that breaks up into the chromium and the oxygen atoms or ions? To keep track of the charge, they came up with this artificial set of rules, and as long as we're consistent about it, it should work out straightforward. And fortunately, most of these rules seem to make a lot of sense. Okay, so the definition for oxidation number, when we compare it to charge, it's the charge an atom would have if the electrons were completely transferred, recognizing that in organic substances or in some polyatomic ions, they're not, right? Covalent bonds, you need some sort of an artificial rule. For free elements, there's no charge at all, right? So magnesium is 0, right? It hasn't given up any electrons. It's uncharged, right? H2, O2, there's no charge on anything. It's just 0. So the examples there, all those shown, have a charge of 0. Which of these have a charge of 0? No, yes, yes, no, yes, no, yes, no, because it's charged. So we should have circled those ones. For ions, in general, it's the charge of that ion, right? For monatomic. If it's polyatomic, we're going to break it down, right? The overall charge for, say, a phosphate would be -3, but we're going to break it down into the phosphorus and the oxygen to make sure everything works out. So lithium is +1, iron 3+ is +3, oxygen 2- is 2-, excuse me. So that's how you do that. It's very easy. Now for oxygen altogether, there is a time where it's -1, but it's really rare, and that's when it's a peroxide, right? So if it's the oxide, that's -2. The peroxide is -1 for each, right? O2, 2-. And for O2, it would be 0, as shown right up here. If it was O2, it would be 0. For hydrogen, well, if it's H2, we learned up here, it's going to be 0. But if it's HCl, that's +1. But there's also hydrides. After all, you have a full outer shell if you have no electrons at all, as you do when you have H+, but you have a full outer shell if you have both of them. If it's H-, we call that a hydride. So hydrogen is +1 when it's H+, and when it's H-, it's -1. It can be either one. H+ is far more common. If it's a group 1 or a group 2 cation, it's always going to be +1 or +2. And fortunately, fluorine, without exception, seems to always be -1. Chlorides and bromides and iodides do weird things where they can get lots of different charges, and we'll show those by example. The rule for the total oxidation number is always equal to the overall charge. So a phosphate, PO4, is overall going to be -3 because its charge is -3, and so you have to account for that. And when we do examples, you'll learn it. You can click on the site if you want to go a little bit deeper. Now we're going to do it again, and I'd like you to try to use this more as a self-test. What is oxidation number? That's the charge an atom would have if the electrons were completely transferred. What about free elements in an uncombined state? I guess we can't really self-test this, but they're oxidation number is 0. Give me an example. Magnesium, beryllium, something like that, right? Neon. If it's a monatomic ion, we're just going to match the charge. So Li +1 is +1. Those are really easy, right? Look at that. If it's oxygen, it's usually -2. For a peroxide, each is -1. So either the peroxide anion or hydrogen peroxide, each of those oxygens is only -1. Very rare. Oxygens are usually -2. Hydrogen is +1, except if it's a hydride, in which case it's -1. Of course, if it's a hydrogen molecule, it's 0. Group 1A metals are +1, 2A metals are +2, fluorine's always -1. This sounds exactly like the last time. And then we have the total charge matches the total charge of the molecule or ion. Let's do some oxidation numbers of each. Notice overall uncharged, overall -2. So each lithium, we know those are group 1, so each one of those is +1. The oxide is -2. Oh, and there's a strange one. This is a new rule. We didn't see this last time. Occasionally you can get values that are not integers. The O2 -1 is very rare, but it's not O2 -2, which showed up right there. It's O2 -1, a superoxide. It's got a charge of -0.5. Ooh. Okay, this one, as we said, is +1 and -2. Can you give me the charge of hydrogen, nitrogen, and oxygen? Well, there's no charges, so there's nothing fancy going on. Hydrogen, that's the H+, so +1. Nitrogen, group 5. So those are always -3, I believe, right? And oxygen, each of them is -2. Let's see if that adds up. Yeah, look at that. +5. Oh boy, it's been a while since I've done this. Nitrogen is not -5, it's +5. It's not -3, it's +5. Okay, so we'll have to remember that. Chromium, well, we don't know because that's in a polyvalent region. Each oxygen is -2. That totals up -14. So we have to have this equal to -12. Each one of those must be +6. Get it?
Message is received from Shirley Louise May.
And there you go. So that is a little bit about oxidation numbers.